Thank
All
you.
right, so let's go ahead and start off with our last chapter that we're going to discuss, which is chapter 11. And chapter 11 talks about gases. We have a whole chapter discussing gases. Remember the different states of matter? We had solid, liquid, and gases. We know the most about gases, so we got a whole chapter devoted to gases. A few things we have to remember about gases is that gases are compressible. And which really means they have no fixed shape or volume. All right, so we got to remember that gases, they're easily compressible. Think about when you're pumping up the tire for your bike. You have a tire pump and you can press the pump in and out. That's what I mean by gases are compressible. A few things also I want to point out is that gases have a low density. They have a low density compared to their solids and liquids. So if we're talking about the same substance, let's say, for instance, we're talking about water. You know, we have liquid water, and then when water turns into a solid, it's ice. But when water turns into a gas, we call it water vapors. I'm saying that the density of the water vapors is much lower than that of the water and of the ice. So that's why gas particles float above us. So think about our atmosphere. Our atmosphere is made up of gas particles. And remember, the less dense things float above. So the gas particles float above our heads. All right, so to understand gases, we first have to talk about pressure. And all pressure is, because when we do gas calculations, we're gonna do it in terms of pressure. And all pressure is the force exerted per unit. Are you listening? Per unit area by gas molecule as it strikes the surfaces around them. So I'm saying that the pressure is equal to the force over an area. And all this really means is I'm saying that, let's think if I have a closed container, I have a jar full of gas particles and it's closed. What ends up happening is these really tiny particles that are the gas particles are moving very fast. Although we can't see it, they're moving very fast and they're constantly colliding with each other. And when they collide with each other, they then hit the walls of the container that they're being held in. So they're gonna bounce off each other and then bounce off the containers of the jar. And when they bounce off the containers of the jar, that's how pressure is built up. So the more particles and the faster they're moving, the more they hit the surfaces of the containers, and that's how pressure builds up. So it's saying a force over an area, and the units of pressure, which we're going to talk about, or which we need to know. The units, the first one I'm going to talk about is an atmosphere. So atmosphere is an ATM, that's the abbreviation for it. Jeez. All right, so an atmosphere is defined as the average pressure at sea level. And it's approximately 1 atmosphere, or around 1 atmosphere. So you might see like 0.99 atmosphere, 0.98 or 0.97 atmosphere. It's around 1 atmosphere. So this is the unit we're gonna most commonly see, the one we're gonna most commonly work with. It is not the SI unit, but it is the one that we're gonna most commonly work with. The second unit that you're gonna see a lot is millimeters of mercury. And it's literally what it sounds like. We're measuring the millimeters of mercury. So the abbreviation for millimeters of mercury is MM for millimeter, and then HG for mercury. Another name for millimeters of mercury is the torr. And millimeters of mercury come from a device called the barometer. And all a barometer is saying that if I have a glass little open container of liquid mercury inside, if I put a tube in that container, remember mercury is a liquid at room temperature. It's the only metal that's a liquid at room temperature. If I put a tube inside, upside down like this, of this container full of mercury, the mercury at sea level will rise up this tube all the way to 760 millimeters. So this whole device is called a barometer. And we can say that 1 atmosphere is equal to 760 millimeters of mercury from this device. Or we can say 760 torr. And torr is another name of it because the Italian scientist that came up with the barometer, his name was like Torricelli or something. So we can call it a torr, or we can call it millimeters of mercury. It's just saying that at 1 atmosphere, which is the pressure at sea level, mercury will rise up this tube 760 millimeters. All right, so the third unit you'll see is a Pascal. And the Pascal is abbreviated as PA. And it is the SI unit of pressure. International. All right, so the SI unit is a Pascal, and we can say that 1 atmosphere is equal to 101,325 pascals. And since that number is so big, another way you might see it is saying it's also equal to 101.325 kilopascals. So K pascals, remember, is a prefix multiplier. The K stands for kilo. Just like a kilometer, we can have a kilopascal. And then finally, a unit you might see is pounds per square inch. And that is abbreviated as PSI. All right, just to refresh our memory, let's just do a quick conversion to make sure we can convert our units of pressure. So you guys spend a second and see if you can work out this problem. This is an example of a simple problem that will come up on the final exam, is if I need to convert 275 kilopascals to millimeters of mercury. So you guys spend a second and let's see if we can set this conversion up properly. Okay, guys, were we able to set it up?
I got 2060 mmSg.
Okay, well, let's talk it through. So just to remind us, we have kilopascals and we're trying to go to millimeters of mercury. I don't have a conversion from kilopascals to millimeters of mercury, so what should I go to first?
Atmosphere.
Atmosphere. All right, so I'm gonna say 275 kilopascals. And I'm gonna say my first step is to go from kilopascals to atmosphere. All right, the conversion just says it right up here. 1 atmosphere equals 101.325 kilopascals. So 1 atmosphere, 101.325. All right, so I'm out of kilopascals. And now my second step says I'm gonna go from kilopascals to millimeters of mercury. I'm sorry, atmosphere to millimeters of mercury. So now atmosphere here at the bottom, millimeters of mercury at the top. 1 atmosphere equals 760 millimeters of mercury. What'd you guys say you got with 3 sig figs in your answer?
2060.
2060? Can I get someone to second that?
I second that.
Okay, perfect. Or we can write it in scientific notation. If we write it in scientific notation, we're saying 2.06 times 10 to the power of 3 millimeters of mercury. All right. All right, so let's get into these gas laws. So these are the units we're gonna use. Anytime you see these units, you gotta know we're talking about gases. And let's go from there. Do I have any questions before I keep going? All right. So these gas laws, I'm gonna start with the simple gas laws. Simple gas laws. All right, the simple gas laws, we have a few of these. They basically show the relationship between pressure, volume, and temperature and amount in different ways. The first gas law I'm going to start off with is Boyle's law. All right, so Boyle's law is says that the volume of a gas is inversely related to the pressure of a gas at constant temperature and constant amount of moles. And before, when we talked about moles, we abbreviated it as MOL or just wrote out the word moles. Now we're gonna say that the variable for moles is the lowercase letter n. So what this is saying is that the volume and the pressure of a gas are inversely related, meaning as one goes up, the other goes down. So we can use an equation that relates these two, pressure and volume. And that equation says, if I have an initial pressure and I multiply it times an initial volume, when I change one of the others, I can say the final pressure times the final volume, they're going to be equal to each other. So when we think about Boyle's law, I have an example for it, but when we think about Boyle's law, we can use bike pump again. So think of a tire pump and you're pressing it in and out. As you press the pump down, when you press the pump down, it ends up increasing the pressure, but when you increase the pressure, when you press the pump down, it ends up decreasing the volume inside of the pump. But as you pull the pump lever up, it decreases the pressure and it increases the volume inside of the pump. So that's all this is saying is when one goes up, the other goes down. And the equation we can use to relate these two is P1 V1 equals P2 V2. So let me give you an example of what I mean. So let's say if, let's say I have this high performing, no, I don't like that example. Let's say if 22.5 liters of nitrogen gas remember, nitrogen gas is written as N2 at 748 millimeters of mercury. Are decompressed to 725 millimeters of mercury at constant temperature. What is the new volume? All right, so when we look at this, we have some nitrogen gas. It's saying its initial pressure is 748 millimeters of mercury. Then it decreases to 725 millimeters of mercury. And all this is happening at constant temperature. What is the new volume? So basically, I know my initial volume, I know my initial pressure, I know my final pressure, and I want to know my final volume. So I can use this relationship, and this time I'm going to try to solve for V2, which is my final volume. So we have to do some algebra to rearrange the equation, or we can just all plug it in together. But basically what this is saying is if I start off with 22.5 liters as my volume, that's my V1, my pressure is, my initial pressure is 748 millimeters of mercury. My final pressure is 725 millimeters of mercury. And I want to know my final volume. So this is what I'm looking for, my V2. It's like my X.
Are these multiplied? Is that the implication?
Parentheses saying that they're multiplied by each other. And what is actually happening is saying when I multiply the pressure times the volume, the number of particles is going to be the same. So it doesn't matter what I do. If I increase the pressure, the volume is going to go down. If I decrease the pressure, the volume is going to go up, but the number of particles is going to be the same. And so I end up, I can use this relationship by saying, multiplying them together. So 22.5, let's pull out my calculator, 22.5 times 748 is going to give me, on this side, I'm going to get 16,830. And remember, we're still working off sig figs, but we're not going to round into the end. So that's saying 3 sig figs here, 3 sig figs there. And then this side is saying 725 times V2 now. So to solve for V2, I just have to do the opposite of what's happening. The opposite is being divided. So I'm going to divide both sides by 725. If I divide by both sides by 725, I end up getting what? 23.2, and this is liters. So these simple gas law equations are just saying, I'm going to know 2 different variables. I'm going to know my volume and my pressure in the case of Boyle's law. If one changes, I should predict how it's going to affect the other one, just by using this equation. I know to use this equation because I'm given a volume and I'm given an initial pressure. I'm sorry, an initial pressure and a final pressure, and I'm asked to find the final volume. So when I have a beginning something and I'm looking for the final, I know to use this gas law. And this one relates pressure and volume. All right, any questions before I go on to the next one? The next gas law. All right, so this was the first one. This is Boyle's law. It says P1 V1 equals P2 V2. The second one that I want to talk about is going to be Charles's law. I have a few to talk about, but they're simple gas laws, and then I'll give you an easy way to remember them all. So the second one says, it's called Charles's law. Charles's law says that the volume of a gas is directly related to the temperature. And this is the temperature in Kelvin. So the Kelvin temperature of a gas at constant pressure and amount of moles. The amount of moles is given by N, once again. All right, so with Charles's law, what it's saying is that if the temperature of a gas is doubled, the volume of the gas is doubled as well. So the equation we can use for Charles's law that relates these two variables says that the initial volume divided by the initial temperature is equal to the final volume divided by the final temperature. You have to remember that your temperature needs to be in Kelvin. You guys remember the equation for Kelvin if we want to go from degrees Celsius, because a lot of times the question will ask you in degrees Celsius. Kelvin is equal to degrees Celsius plus 273.15. All right, so let's do a quick example with Charles's law. My example with Charles's law says I have a sample of gas, has a volume of 2.80 liters at an unknown temperature. When the sample is submerged in ice water at temperature equals 0 degrees Celsius, its volume decreases to 2.57 liters. What was the initial temperature in kelvins? All right, so we are given a volume and a temperature, and we're given an initial volume and a final volume, and we are given a final temperature, and we're asked to find the initial temperature. So if I'm given volume and temperatures that are changing, I know that I can use Charles's law. And to use Charles's law, I just have to remember to set my temperature to kelvins. So in this case, the question says, what was the initial temperature in Kelvin? In this case, we are looking for T1. Now, looking for T1 or T2 or anything in the denominator is the tougher problems. You guys have trouble sometimes rearranging the equation to solve for a variable in the denominator. And so my suggestion is I plug in my numbers, I plug in the value for V2, I plug in the value for T2, and then I get a number here. And then when I do so, I can do the opposite. So my final goal is to get T1 at the top. So to get T1 at the top, what I'm saying is, if I just want to solve for T1, it needs to look like this. Basically, I have to, we get this number and then we divide this number. We basically divide this side by this side. A better way to think of it is I can say T1 is gonna equal to V1 times T2 divided by V2. So basically it's like I'm doing the reciprocal where I take T2 and V2, flip it, and then put it on the other side. But I think an easy way for you guys to do it is to just get a whole number here on this side, like divide these two numbers and then rearrange things. So let's set it up. Let's go ahead and see that T equals 0 degrees Celsius means what in Kelvin, guys?
273.50.
All right, 273.15. So that means that my temperature, my T2 is equal to 273.15 K. It's important that we do that first because if you try to solve, if you plug in 0 into the equation, you're gonna get an answer that says 0, and that's not the correct answer. So we can't plug in our temperature and then change it at the end. We have to change it first and then plug it into the equation. So we changed it to 273.15. All I did was say 0 degrees Celsius plus 273 is gonna give me 273.15 K. So that's my T2. And if I plug everything in, I'm gonna do it like I told you guys to do it. I'm just showing you, ultimately, this is how I get the answer. But I'm gonna say V2 over T2. So I'm gonna write the equation out first. V1 T1 equals V2 over T2. And remember, I'm looking for T1. So I'm saying V1 is gonna be 2.80. And I'm saying that divided by T1 is equal to V2, which in this case is the 2.57 liters, divided by T2, which is the 273.15 K. All right, so my suggestion is saying I take my 2.80 liters over T1. I get a number for this side. When I get a number for this side, I divide those two numbers. I end up getting 0.009408 or so. You guys see this in your calculator. I got a number for this side. And then I have to get T1 at the top. And to get T1 at the top, I have to multiply this side by T1. If I multiply both sides by T1, it's gonna cancel out my T1s. And then we know how to solve it if it's saying 2.80 equals this number times T1. We're gonna divide both sides by this big number right here. So ultimately, it's saying that 2.80 divided by 0.009400875 equals T1. So I'm gonna put that in my calculator, 2.80. You guys following what I'm saying?
Yep.
Yeah, I'm pointing this out step by step because I know this comes up, and although you guys know the equation to use and you know how to set it up, when you go to solve for a variable in the denominator, you guys screw this up a little bit, or not even a little bit, you end up getting the wrong answer. And when you have a multiple choice exam, you know that wrong answer is going to be listed, and it's a common mistake. So I just want to make sure I walk through how to solve for variables in the denominator.
So basically, I'm sorry, you just did 2.80 and you plugged it in So you're doing it basically step by step, right?
Yeah, I'm just doing it step by step. So we see we're solving for T1. I say get a number on this side. So I got that number. When I divide these two numbers, it equals this. And then because I want to get T1 at the top, I multiply by T1 on both sides. And so I ended up getting 2.80 equals this number times T1. So that's like saying 2.80 equals this number times X. And then we solve for X by saying divide both sides by this number. And when we do that, we're going to end up getting T1 equal to, I got 297K. And when we look at our sig figs, I think 3 sig figs is the least amount for all of it. Yep. And remember when we had this 0 degrees Celsius, it was the addition subtraction rule, which says the least amount of decimal places. And the least amount of decimal places was no decimal place because 0 had no decimal places. So that answer technically should have just been 273, which would have been 3 sig figs. So the answer altogether is, oh, it's 297.59. So maybe it's 298 is the answer. 298.
That's what I got.
Yeah. All right, so let me know if you guys have any questions on what I just did.
Did you multiply or did you divide?
Where, which step are you talking about? Here at the bottom?
Yes.
I divided 2.80 divided by this number.
Oh, okay. I'm getting something different. I don't know what I'm doing wrong.
When you divide these two numbers, 2.80 divided by this, what are you getting?
I got 29.75. I'm not sure why.
I'm missing a 0. So this says 0.00.
Oh, okay, I see.
Yeah.
Where are we getting the subtraction from?
Where do you see subtraction?
Where you or wherever? How do you get the decimal places?
This one right here?
At the answer where it has no decimal places.
Oh, okay. Because remember, we want our sig figs. So the sig fig says least amount of sig figs, which is basically just 3. So.
But. Oh, okay.
You see what I mean?
So that's why you didn't need a decimal, because you only had 3 sig figs.
Right. So the answer in my calculator said this. And then I rounded it up. 1, 2, 3.
Oh, okay. I see.
Rounded. Okay.
Okay.
All right. Any other questions? And I have I have a practice worksheet for these type of problems, and there's a 1 or 2 that has you solving for a variable in the denominator. All right, so let me talk about the other gas laws right quickly, the simple gas laws, and then we'll take a break. And all right, so that's Charles's law. I'm going to quickly give you the other ones. The next one says Gay-Lussac's law. Gay-Lussac's law relates pressure and temperature, and it says that the pressure of a gas is directly related to the temperature in kelvins again. The temperature's always got to be in kelvins when we talk about these gas laws. And this is at constant volume and moles. Remember, moles is designated with the letter N. And when we talk about this gas law, when we talk about it's being directly related, basically if one goes up, the other goes up. If the pressure of a gas goes up, the temperature of the gas is gonna go up, or vice versa is a better way to say it. If the temperature of a gas goes up, the pressure is gonna increase as well. So we would say that P1 over T1 is equal to P2 over T2. So it's similar to Charles's law, but instead of it saying volume and temperature, it's going to relate pressure and temperature. And just remember, it's got to be in Kelvin. The temperature's got to be in Kelvin once again. I'm not going to give an example right here. I have a worksheet full of examples. I'm just going to go to the next law. So all this is saying is that anytime you have pressure and temperature in your question, you can use this relation. If one of them changes, the other one's going to change as well, as long as you are at constant volume and the amount of moles. And that way we can use this equation to figure out what the final pressure or the final temperature is going to be. All right, now, even better, we can now combine all these three laws that we just learned, and we have what is known as a combined gas law. I know it's hard to remember all these gas laws sometimes, so the easiest thing to do is just know the combined gas law. The combined gas law is what it sounds like. It combines the three gas laws I just talked about. The first one I talked about was Boyle's law, which said P1 V1 equals P2 V2. The second one I talked about was Charles's law, which said V1 over T1 is equal to V2 over T2. And then this third one is Gay-Lussac's law, which says P1 over T1 is equal to P2 over T2. So if we combine these laws and we can say this is all happening at constant amount of moles, or the amount of the gas just doesn't change. If the amount of gas doesn't change, we can use the combined gas law. And basically, this is the easy one to remember because let's say you don't really remember the relationship for the other laws. If you know this, if the question's asking you about the volume and the temperature and says nothing about the pressure, we can just cover up the pressure and ignore it, and we'll have Charles's law. If the question is asking you about the pressure and the temperature and says nothing about the volume, we can cover up the volumes. If we cover up both the volumes, we'll have Gay-Lussac's law. And if it asks you about the pressure and the volume and says nothing about the temperature, we'll have Boyle's law. So the combined gas law, if you can't remember any of them, I would say remember the combined gas law. You just have to remember the temperature, once again, still needs to be in Kelvin. I'll put that here. Temperature is still in Kelvin. And if it doesn't say anything about any one of the gases, any one of the variables, we can just ignore it. But let me give you an example to where we do use all three variables. Let's do an example with that. So it says a sample of gas has an initial volume of 158 milliliters at a pressure of 735 millimeters of mercury and a temperature of 34 degrees Celsius. If the gas is compressed to a volume of 108 milliliters and heat it to a temperature of 85 degrees Celsius. What is its final pressure in milliliters of mercury? So it's basically saying, what's the final pressure in mmHg? Okay, guys, so when we look at this problem, we are given a volume, a temperature, and a pressure. So if I'm given all three variables, that means I can use the combined gas law. And the combined gas law just simply says P1 V1 over T1 is equal to the final pressure times the final volume over the final temperature. In this case, the question is asking us, what is the final pressure? So we are looking for P2 in this case. And it's asking us millimeters of mercury. Our initial pressure started off in millimeters of mercury, so that's fine. Our initial volume started off in milliliters and it ended in milliliters, sorry, so it's fine. So the only time you really have to change the variables or the units is when you have a temperature that's not in Kelvin. Or let's say, for instance, this volume was in liters and this one was in milliliters. Our units have to be the same for them to cancel each other out. So in this case, they're both in milliliters. Sometimes they give an example where your volume's in liters and one's in milliliters. It doesn't matter which one you convert to. You can convert to liters or you can convert to milliliters. They just have to be the same unit so they can cancel each other out. So if we're gonna solve for P2, I like to just plug all my numbers in and then, you know, get an answer on this side and then get a number on this side and then divide the two. So in this case, we have to first change our 34 degrees Celsius to Kelvin. And then when we do that, has anyone done that? Or can anyone tell me what that is?
Yeah.
7.15.
It's 7 what?
7.15.
307.15, okay, sounds good. So this is technically, what is this? This is my T1. My T1 is gonna be the 307.15. What's my T2?
158.15.
So I'm gonna write it up here just so 307.15 K here. And then if I change 85 to Kelvin, what did we say it was?
58.15.
358.15 K. All right, so I'm just gonna go to plug everything in. My P1 says it's gonna be 735 millimeters of mercury. So 735 millimeters of mercury. My V1 is gonna be my 158 milliliters. My T1 is the 307.15 K. And I set that equal to P2, which is what I'm looking for. And then my V2 is 108 milliliters. And then my T2 is the 358.15 K. So it looks like, once again, I'm gonna need 3 sig figs. When I put this all in my calculator, you know I'm gonna get a number for this side, then I get a number for this side times P2. So I'm saying 735 times 158 divided by 307.15. This side, I ended up getting 378.088, so on. I think that's enough, is equal to, I'm saying 108 divided by 358.15. I ended up getting 0.3015. I'll say 49, and this is all times P2. So most of us can solve for the unknown variable this way. We just do the opposite of what's happening to P2. It's being multiplied, so I'm going to divide both sides by this number. So in this case, what I'm saying is that 378.088 divided by 0.301549 is equal to P2. Once I do this, I can say P2 is equal to, I got in my calculator 1253.819. I need 3 sig figs. When I round this to 3 sig figs, that's 1, 2, 3, and then this is a 3, so I'm going to round it down to 0, so it ends up being 1,250. And this is millimeters of mercury, or we can say 1.25 times 10 to the power of 3 millimeters of mercury. All right, any questions on how I got this answer?
And we got the 3 6 figs from 735, right? Correct?
Yeah, or 108. These both have on, or 158. These all have 3 sig figs.
Okay.
Yeah. All right, and then right before I give you guys a break, the last simple gas law I want to talk about is Avogadro's law. And I'll just tell you what it is. The worksheet that I posted on Brightspace under chapter 11 has 3 example problems or so for each one of these laws. So I'm saying the volume of a gas is directly related to the amount in moles. Remember, that's going to be in. And basically it's saying that if the number of particles increases, that means the volume is going to increase. So the equation we use for this one simply says if the number of particles or the number of moles increases, the volume increases. So if one doubles, the other one will double as well. And this happens at constant temperature and pressure. So anytime you see volume in moles, together, you can use Avogadro's law. All right, so these are simple gas laws. Remember, the one to remember is the combined gas law, if you forget them, and then Avogadro's law is the only one after the combined gas law.